Okay, welcome back. I believe where we stopped last time we were talking about shapes of molecules, so let's go there. So we said that I gave you a sheet, a little handout there. It's in the back of your notes that actually covers the shapes of the molecules, and there's a bunch of different shapes there. That's kind of what we're going to go through here. But the easiest way, instead of just memorizing them all as just different shapes, is to memorize the 5 main shapes first. Once you get those 5 main shapes, all the rest of the shapes are pretty much derived from those 5 main shapes. So that's where I would go first, and then try to figure out what the rest of them look like. So let's take a look at our little handout here. So the 5 main shapes that we want to start with here are your molecules that have shared pairs but no unshared pairs on the central atom. So from our last video, we talked about the VSEPR formula. That would be your AX2, that would be your AX3, your AX4, your AX5, and your AX6. All right. AX2, remember X represents the number of shared pairs on the central atom, E represents the number of unshared pairs. So AX2 means 2 shared pairs, no unshared pairs on the central atom. All right. So what would be an example of an AX2 molecule? Well, that beryllium fluoride that we drew for you back when we were drawing the dot structures would be an example. If you'll remember, the dot structure for beryllium fluoride looked like this, and you'll remember we said that beryllium is one of those exceptions to the rule. It's just perfectly fine with 4 electrons around it. Yeah. Do you see why this is an AX2? Well, you have 1 pair here, 1 pair here, no unshared pairs on the central atom. Lots of unshared pairs, but they don't count. It's the ones on the central atom that you're worried about. Okay? So what it comes down to is I have 2 fluorines to put around a beryllium. How can I get them as far away as I possibly can? Well, let's take our model set that we talked about from last video. So here's my beryllium. You just kind of have to use your imagination when you go cheap on the model set. And here's my 2 fluorines. How can I get these fluorines as far apart from each other as I possibly can, which minimizes the repulsion, which would be the lowest energy state? Well, I could put one on this side, and I could put one on this side, like that. And if I do it like that, what that does is that gets these atoms as far away from each other as possible, and I end up with a shape that looks like this. Now, when I'm determining the best shape, I want to get the atoms, or really, honestly, it's these pairs of electrons I'm trying to get as far away from each other as possible. It is useful to be able to calculate something called the bond angle. All right, and the bond angle is the angle from this bond over to this bond with my vertex right here at the center. So this ends up being a straight line. What's the angle of a straight line? Well, it's 180 degrees. So this has a bond angle of 180 degrees. What am I going to call this? Well, I got 3 atoms. They're all in a line. So I'm probably going to call this linear. And that's exactly what this shape is. This is linear. So when you have an AX2, the shape of that is linear. And that's one of the shapes the main shapes you need to know. Okay? All right. The next shape that we need to talk about is the AX3. All right, that stands for 3 shared pairs, no unshared pairs on the central atom. So an example of an AX3 would be that BH3 molecule that we drew for you. Okay, so that's notice that I've got 3 shared pairs, no unshared pairs on that boron. Remember, boron's happy with 6 electrons. It's okay with that. So we drew it kind of like a T shape there. But is that really what it looks like? You know, does it really look like this? Is there any way I can get those atoms further apart from each other? Well, I can. So let me play with it here. Let's see what we can do. So maybe I do something along these lines. Put that there. Put that there, and then maybe this one over here. And so I get something that looks similar to that, right? here's my boron in the middle, here's my 3 hydrogens. And that's as far apart as I can get them. It's just like this. Alright? Well, when you name the shape, you don't really look at the individual atoms. What you do is you look at the entire solid figure that's formed. So imagine if you wrap this thing in aluminum foil, what would you get? Well, you get a triangle here. See? And it would also be flat. It would be planar. Okay, so what are we going to call this? Trigonal planar. And that is the shape of an AX3, which an example of that would be the BH3. Okay? Bond angles. What are the bond angles here? Well, this angle to this angle. Notice that I have cut an entire circle into 3 pieces. 1, 2, 3. How many degrees are there in a full circle? There's 360. 360 divided by 3, 120. So your bond angles in an AX3 are 120 degrees. Alright, so you never thought you'd use that geometry you had to take, right? Back in high school? Yeah, well, here it is. Okay? Your AX3 and your AX2E both belong to the AX3 family because you have 3 pairs of electrons. It's just that they're not all being shared. So sometimes they'll say both of these have the same electronic geometry, AX3 electronic geometry. The molecular geometry is AX3 and AX2E. We're going to skip this one for a while. And we're going to go down to the AX4. Okay. So an example of the AX4 would be, well, it'd be that formaldehyde, that trichloromethane that we drew for you when we were doing dot structures. Remember that one? And you came up with something that looked like this? Well, this is actually an AX4 molecule. Do you see why it's an AX4? Because I have 1, 2, 3, 4 shared pairs, no unshared pairs on that central atom, on that carbon. Alright? And we drew it, and we made it look like a big giant flat square. Alright? What would the bond angles be if it was a big giant flat square? Well, it'd be 90 degrees, right? What if I could show you a shape that had a bond angle greater than 90 degrees? Would you agree with me that it's a better shape? Okay. I'll take that as a yes. All right, well, let's see what we can do here. Get this built pretty quickly so I'm not wasting valuable video time. It's not bad. Pretty good for a first try. Hopefully you can see it. I know it's on a flat computer screen, so it just takes all the three-dimensional fun out of it. But basically you get something that looks like this. And if I had made it correctly, I could actually turn it up like this, or I could turn it like this. And you know what? This is actually, I gotta say, it's pretty good for a first attempt. Okay, it's a little crooked there. But it should look exactly the same no matter how I turn it. Okay? And look at these bond angles. You see that this would be 90 degrees right here. You see that's greater than 90 degrees? That's greater than 90 degrees. That one is greater than 90 degrees. From here to here. Trying to get to the camera. So yeah, this is a better shape than just a big flat square. Okay? So what am I going to call this thing? Well, again, it's not the number of bonds. Wrap it in aluminum foil and look at the solid shape you make when you do that. If you do that, what you'll see is you've got yourself a little pyramid here. Okay? You've got a triangular base. That's here to here to there to there. I know, kind of hard to see. Triangular base. And then you've got 1, 2, 3 triangular faces. Alright, so when you have a shape that has 4 faces with 4 equilateral triangles, a little pyramid like that, that's called a tetrahedron. Okay? And so therefore you call this shape tetrahedral. And that's the shape. And that is actually the same shape as that methane molecule, that CH4 that I showed you in the last video. That's actually a much better one than I can make. But again, if you can make it, you understand it. So that's why I think it's good for you to get you some styrofoam balls and build these things. It'll help you visualize it a lot easier. But yeah, it looks just like this. Okay? It's not flat because I can get greater bond angles. See, molecules are three-dimensional. They're just like you and me. They're not flat little planar things like we draw them on the board, sometimes. But yeah, this is what it looks like. So how would I draw something like that? Well, one way you could do it is you could do it this way. You don't have to be an art major to pass this class. What you could do is you could draw your 3 chlorines down here, sort of like the base of my little pyramid here, and then put your hydrogen on top. And I would take that, okay, because that tells me you know it's not flat like this. All right. Here's something called the dash line wedge system. All right. In the dash line wedge system, this is a way to represent a three-dimensional molecule in 2 dimensions. If you see a bond that is in the plane, flat, then you draw that as a line. All right. If the bond is coming out towards you, then you draw that as a wedge. If the bond is going back away from you, you draw that as a dashed line. So what I can do is I can take this molecule and I can twist it like this, where these are in the plane. So in other words, these 3 atoms right here, this one, and this one, are all in the same plane. Okay? If I do that, this is my hydrogen. It's in the plane. This is my chlorine. It's in the plane. I have one chlorine that is coming out towards you. That's that wedge. And I have one chlorine that's going back away from you. And that's that dash. And so this is another way to three-dimensionally represent the shape of this. I would take this, or I would take this, if I asked you for the shape. Now, if I asked you for the dot structure, you can draw it this way, because that's just a dot structure. But if I say draw it in the correct shape, or I said what's the shape, you can't draw it like this because I need to know you know that's not flat. It's three-dimensional. All right? All right. Bond angle-wise, you can sit there all day trying to derive this. I really think it's just much easier if I tell you 109.5. That's the bond angle. That's a really important bond angle in organic chemistry because remember we said carbon always forms 4 bonds? Well, if you've got a carbon single bonded to a bunch of stuff, it's going to be an AX4. It's that bond angle 109.5 comes up quite a bit in organic chemistry. So yeah, it's worth knowing. Okay? All right, we're going to skip the others here. These 2 belong to the AX4 family because there's 4 electrons, or 4 pairs around them. They all have an AX4 electronic geometry. Okay, I use the term family, but whatever. They have different molecular geometries, different shapes because of those unshared pairs. But we're going to come back to it. Don't worry about it. Okay? All right. Next family. That would be your AX5. Okay? AX5 stands for 5 shared pairs, no unshared pairs on the central atom. All right. A good example of that would be a phosphorus pentaiodide. All right. Everything on this back page, by the way, what they have in common is they're all expanded octet molecules. Obviously, if I have 5 pairs of electrons around the central atom, I have more than 8 electrons. Okay, but these are all expanded octet type molecules. So a phosphorus pentaiodide, Pi5, would be an example of that. Dot structure-wise, it looks like this. If you drew it, and I know you can draw the dot structure at this point. Okay, how do I represent the shape? Well, the shape looks something like this, and here's how you build it. So, do you remember the AX3, which was the trigonal planar, right? There we go. So, build yourself an AX3, a trigonal planar, okay? And then set it up like this. So, it's sitting kind of flat, all right? Take one ball and put on top, like that, and then take one ball and put on the bottom, like that. And that is what phosphorus pentaiodide looks like. Good luck drawing that, right? Well, it's not as bad as it looks. Here's what you're going to do. you're going to take it and you're going to turn it like this, so that these three atoms here are all in the same plane. Okay? And then you're going to have one atom that's coming out towards you, and you're going to have one atom that's going back away from you. So when you draw it, it looks a little something like this. This is in the plane, this is in the plane, this is also in the plane. Makes a big T. And you've got one coming out, one going away. If you draw these two kind of closer together than the rest, then it gives it some perspective. Okay? If you want to do dash line wedge, you can set it up like we said. This is in the plane, this is in the plane, this is in the plane. Okay, in the paper, so it's like a T. And then you've got one atom coming out towards you, and you've got one atom going away. So there's your wedge, and there's your dash. Okay? To name this, wrap it in aluminum foil. So what have I got here? Well, what I have is, if I took this bottom one off right here, like that, what would I have? Well, I've got a little pyramid. See, here's the base down here on the bottom. I know with the camera it's kind of hard to see. But there's the base. 1, 2, 3. Okay? And then here's a face over here. Here's a face there, and there's a face back here in the back. You just got to trust me on that. All right? So it's like a little triangular pyramid. Okay? If I took the top off, what have I got? Well, I've got exactly the same thing. It's just upside down. See? So essentially, I've got a triangular pyramid here, and then I've got a triangular pyramid here, and it's like I stuck them base to base. I end up with a shape that looks somewhere along the lines. I'm trying to figure out this way with the camera. Somewhere along the lines of this. Okay? So we call this trigonal bipyramidal, not to be confused with trigonal pyramidal, which is an AX3D. All right, but that's where the name comes from. All right, bond angle wise, this one's a little more tricky. All right, because there's actually 3 bond angles here. All right, imagine this was a spinning globe. So it's just kind of twirling along right here. Okay? Well, you've got an atom up here going toward the North Pole. Got a North Pole atom up here. You've got an atom down here on the South Pole. So there's an atom down there. And then you have these 3 atoms which are kind of going around the equator. Okay? These 2 positions are called axial positions because, well, they're on the axis of rotation here. These 3 positions are called equatorial positions because they're out along the equator of my little spinning globe. Okay? So I've got 3 bond angles here. I've got an axial bond angle, which would be basically from the North Pole all the way down to the South Pole. Well, that's a straight line, so what's that angle? Well, that's 180 degrees. All right, so you've got an axial. You've got an equatorial bond angle, which is essentially the angle from here over to here. Okay? Well, again, I have cut my circle into 3 equal parts, and so therefore 360 divided by 3, 120. It looks a lot better in person. I apologize for the camera, but that's just what we're stuck with, I guess. So build it. Make more sense. All right. So you got 120 here, and that's an equatorial bond angle. All right. And then you've got an axial equatorial angle, which essentially is here to the equator. Well, that's halfway from here down to the South Pole. So this bond angle here is what? That's 90 degrees. All right. So your bond angles are 180, 120, and 90. Axial is 180, equatorial is 120, and axial equatorial is 90. And those are your bond angles on a trigonal bipyramidal. Okay? Your AX4E, your AX3E2, and your AX2E3 all belong to the AX5 family because you have 5 pairs. There's not being shared. So we'll skip those for now, and we'll go to the last one of the families here, and that would be your AX6 family. That stands for 6 shared pairs, no unshared pairs on the central atom. An example of that would be this molecule, and that's SF6. This is sulfur hexafluoride. Sulfur hexafluoride, if you drew the dot structure, would look like this, and of course you can put the dots in around the fluorine. I didn't do that, but you have essentially 1, 2, 3, 4, 5, 6 shared pairs, no unshared pairs, sitting on that central atom. That's what makes it an AX6. All right. Is the shape of it, does it look like a big giant flat wagon wheel? No, it doesn't. So how do I build this one? Well, I need some more styrofoam balls, I guess. Well, here's what you do. Remember how you made a triangle last time? And put one on top and one on bottom? Well, this time what I want you to do is I want you to build yourself a square. You can build a square, can't you? You might be an engineer to do this. Might help, I don't know. Yeah, apparently I can't. My styrofoam balls are getting a little chewed up. I need to invest in a new molecular model set. But okay, that's pretty close. It's the camera angle. This is a perfect square. It's just the camera makes it look a little odd. So. Okay, so we built ourselves a big square. So what are we going to do now? Well, what we're going to do is we're going to put one on top. And we're going to put one on bottom. And you get a shape that looks something along the lines of this. And this, if I built it correctly, no matter how I turn it, it should be perfectly symmetrical. You should see exactly the same thing. Alright? And so what it looks like is it looks like a jack. You know, something like that. Or it's an XYZ coordinate system if you happen to be more mathematically minded. But that's pretty much what it looks like. Okay? What are we going to call this thing? Well, again, it's not how many bonds you have, it's the solid shape it makes. So wrap it in aluminum foil, and what you get is you get a solid shape that has a triangular face here. You have a triangular face here. You've got one back here, and then you've got one over here. So you have 1, 2, 3, 4 triangular faces around the top. You've also got a triangular face down here. You've got one over here, and you have a triangular face down here, and you have one down here toward me. Okay? So you have a solid shape here that has 8 triangular faces on it. What are we going to call a solid shape that has 8 triangular faces? Well, that's called an octahedron. So therefore, this molecule is called octahedral, the shape is. And that's what SF6, sulfur hexafluoride, looks like. It looks like this. Okay? It's octahedral because of the faces. You know, there's not 8 bonds. It's not how many bonds you've got, it's the solid shape the molecule makes. And that's why it's called octahedral. Alright? Bond angles, considerably easier. Look at all these 90-degree angles here. See, I got 90 and 90 and 90 and 90 and 90. And then, of course, I guess I also have a 180 here as well. You know, here to there and there to there. The 90 is probably the one that's a little more important. But, yeah, your bond angles here are 90 and 180. And that's an octahedral molecule. How do I draw this thing? Well, you're going to turn it like this, where these 3 atoms here are in the plane. You have 2 of these that are coming out towards you. And then you have 2 of these back here which are going back away from you. So, one way you could draw it is you could draw it this way. You could put these 2 close together and these 2 close together. And that kind of represents that these 4 atoms are all in the same plane. I've seen books where they'll draw lines here to illustrate they're in the same plane. I don't like that because it tends to lead people to believe that these fluorines are bonded together. And they're not. They're just bonded to the sulfur. Okay, but they're in the same plane, same flat plane. Okay, then put one on top, one on bottom. There you go. You got yourself an octahedral. So you don't have to be an art major to do this. If you want to do dashed line wedge, turn it as we said, where these two are coming towards you and these two are kind of going away. And so here's the three atoms that are in the plane, top and bottom, and the sulfur. Here are your two fluorines that are coming towards you. That's the wedge. And there's your two fluorines that are going back away from you. And that's your dashed line. And that's your octahedral. Bond angles 90 and 180. Make sense? So, AX2 linear, AX3 trigonal planar, bond angles of 180 and 120 respectively. AX4 tetrahedral, bond angle 109.5. AX5 trigonal bipyramidal, bond angles of 90, 120, and 180. And then AX6 octahedral, bond angles of 90 and 180. And those are the five main shapes. And that's where you need to start. Okay? All right, well, once you got those five main shapes done, now we can start throwing unshared pairs into the mix and see what happens there. Okay, so let's do a couple here, and I'm going to let you fill in the rest, because you can find examples for this in your book. Probably do you some good to fill it in and try to draw it anyway. So let's take a look at an AX3E. Okay, your AX3E comes from your tetrahedral family, because you have four pairs of electrons around the central atom. It's just that they're not all being shared. AX3E means three shared pairs, one unshared pair on the central atom. Okay? So an example of that would be ammonia, NH3. If you drew the dot structure for ammonia, which I know you can do, you'll find it looks something like this. Do you see why this is an AX3E? Three shared pairs, one unshared pair on the central atom. Okay? Does it really look like this? Well, no, it doesn't. So what does it look like? Well, the shape of everything within the same family, the shape here with these that have the same what we call electronic geometry, four pairs around it, is derived from the main shape of the family. So the main shape in this family is tetrahedral. So what we're going to do, instead of sitting there building another one, I think I'm just going to use this little guy, which I had lying around. I could build it, but why not just use this one? It's nicer, right? So here's my little AX4. What's the difference between a CH4, which would have 1, 2, 3, 4 hydrogens around it, and this NH3? Well, basically, that. See, here's my nitrogen. Here's my unshared pair of electrons sitting on that nitrogen. Here's my three hydrogens here. Okay? Notice these three hydrogens are not in the same plane. This isn't flat. Okay? Why is this not flat? Why isn't this like a BH3 or something like that? Well, because I got this lone pair of electrons sitting up here on top, and that's forcing these three atoms down out of the plane. And so they end up down instead of being flat. So the lone pairs influence the geometry of the molecule. They repel just like the shared pairs. All right? But when you name the shape, you don't look at the unshared pair. So we're going to look at the shape of this molecule, and we're going to pretend it looks like this. So what we've got, wrap it in aluminum foil, make yourself a solid shape. You've got a little pyramid here. See, here's your triangular base on the bottom, 1, 2, 3. Here's a triangular face. There's one in the back here, trust me. And then there's one over here as well. So I have three triangular faces with a triangular base. Okay? This is called trigonal pyramidal, not to be confused with trigonal bipyramidal. All right? And notice the shape is derived from the tetrahedral, because that's what family it belongs to. So this has an AX4 electronic geometry, but its molecular geometry is AX3E. That's what determines its actual shape. What do you think these bond angles are? Well, they come from that tetrahedral. What's the bond angle on the tetrahedral? It's 109.5. So what do you think these are? Pretty close to 109.5. Right. In reality, for ammonia, it's actually 107, because these unshared pairs actually technically repel a little bit more than the shared pairs, and that forces these atoms down a little bit more. And so it's actually not quite 109.5, it's actually 107. But you know, if you want to, you can buy yourself a $5,000 software program called Gaussian, probably up to Gaussian 20 now, and you can do molecular modeling calculations and figure out that exact bond angle. But we're going to assume that the lone pairs repel pretty much as the shared pairs. We're not going to worry about the sizes of the atoms and steric hindrance and all that junk. We're going to call it 109.5 because that's close enough. Okay? So yeah, 109.5. And that's kind of how that looks. Drawing it, basically just draw a tetrahedral, see? And then just erase this one off the top and just put a pair of electrons right there. And there you go. There's your shape. Make sense? Okay. Let's look at this one. Here's an AX2E2. All right, AX2E2. Can I think of an example of a molecule that's an AX2E2? How about water? H2O. See? Look, here's two shared pairs. Here's two unshared pairs on the central atom. Now, we drew it to look like this. Does water really look like this? Or does it look like this? Does it matter? Yes, actually it does matter what water looks like. Is this a better dot structure than that? No, they're equally valid as dot structures, right? So what does water look like? Well, this belongs to the AX4 family, so its shape is derived from the AX4, which is your tetrahedral. So what's the difference between a tetrahedral and a water molecule? Well, basically, that. So see, you've got one pair of electrons on that oxygen coming out behind you back here, and you've got one pair coming straight up at you there at the camera, see? And then these are all on the same plane. Flat. And that's what water looks like. And you've probably drawn it that way before, at least seen it drawn that way before, but now you know why. Okay? This is why your hydrogens aren't straight across. It's because you've got these two pairs of electrons here also interacting and forcing them kind of down onto the plane. Again, they're there, they influence the geometry, but you don't look at them when you name the shape of the molecule. So cover them up, or take them out if you want to. What have you got? Well, you've got three atoms, and they're kind of in a line, but it's not really a straight line. It's more of a bent line. So what are we going to call this? Well, this is bent 109.5. Why is it bent 109.5? Well, what's this bond angle? 109.5, because it's derived from that tetrahedral. Do you see that everything in the same family has the same bond angle? So if you know the bond angle of the main shape, you can figure out the bond angle of everything else in the family. Again, there's a reason why that's true. We'll talk about it next chapter. But yeah, that's the way it works. And so this is why a water molecule looks the way it does, is because of these two unshared pairs. They're not actually sitting one above and below. They're actually kind of over here on the same side of the molecule. And so this is a better representation. But really, this pair would be coming out towards you. This pair would be going away. If you wanted to draw it dash line wedge, there's one way you could do it. See, just draw you a tetrahedral and then erase one of these over here, put a pair of electrons there, erase one of these, put a pair of electrons there. There's your bent, see? So this would look more like that, I guess. But it's still the same thing as this, isn't it? Okay? So, does it matter? Who cares, right? Well, yes, it does make a big difference. You know, the fact that water looks like this. We'll talk about it at the end of the chapter. We'll talk about when we start talking about polarity and such things. But that's the shape, and that's the reason why it is the shape it is. Now, can I determine the shape of this molecule by looking at the dot structure? Is this dot structure any better than this dot structure? No, I've got 8 electrons around each oxygen here, and I got 2 around the hydrogen. This dot structure isn't any better than this dot structure. So is it possible to look at the dot structure and determine the shape of a molecule? No. Is it possible to look at the dot structure in one more thing and determine the shape of the molecule? Yes. So you got to have the dot structure, but you got to know a little something about the VSEPR formula. All right. Now it is critical for you to understand, if you don't have the correct dot structure, then you can't get the correct VSEPR formula. If you can't get the correct VSEPR formula, you can't get the right shape. By the way, if you can't get the right shape, you're going to miss what we're going to talk about in the next video. So it's really critical that you're good at drawing dot structures. It could cause you to mess up everything. Make sure you can get those dot structures down. All right? But if you have the dot structures and you know something about the VSEPR formula, the stuff that we're talking about here, yeah, you can actually determine the shapes of molecules. Make sense? Okay, well that's a good place, I believe, to stop. What we'll do is we're going to talk about a couple of more, but what we're going to do is we're going to kind of extend this into our expanded octet molecules over here on this next page. And so I'll show you an example maybe from the AX5 family and maybe one or two from the AX6 family. I'll let you fill in all the rest of them, and then we'll move on from there. So I know I can get this done in one more video. I know it's going to happen. I will make it happen. So if you suffered through it this long, you really only have one more video to go. So hang in there. You're just about done. So I guess we'll see you next time. We'll continue our discussion from here. So I guess take care of yourself, and I'll get this thing on real quick and get the last one up for you, okay? All right, see you then.